Good morning, everyone. So I took a look at the solutions that people had submitted for homework 7, and I did manage to find one reasonably good solution that the student was willing to share with the class as potential starter code for homework 8. But overall, it looks like people did have a certain amount of trouble getting complete solutions. There are a bunch of almost there solutions, but people had some trouble getting complete solutions to the homework 7 problem. And I think that was just because there's too many moving parts altogether, especially with the having to deal with an error model and having to deal with path following and obstacle avoidance and a bunch of other fun stuff that is all important stuff to figure out, but just ended up being a bunch of stuff for people to figure out all at once on homework 7. So I wanted to provide some clean starter code for homework 8. And so I went ahead and put together something that should at least be a reasonable starter code to help illustrate some of the ideas from homework 6 and homework 7 that you're going to need to get a working homework 8. So let me go ahead and take a look at this Git repository. So what I'm going to do is I started with the homework 6 starter code, and I sequentially edited it to get what I want as starter code for homework 8. So starting from the homework 6 starter code, the first thing that I did was, that's the homework 6 starter code. That's not terribly interesting. The first thing that I did is fixed up the homework 6 starter code so that it doesn't segfault and sped up the build. The changes that I needed for that are changes that for speeding up the, for avoiding the segfaults and just getting nice clean UI code, I just used the techniques that we covered in in-person lecture, but let me go ahead and take a look at those. So I got rid of all the references to mutexes in the visualization module, because in modern GTK recommended style, mutexes aren't used in favor of doing the set idle handler call, which schedules tasks to run on the UI thread, so that all of the UI thread is running single-threaded, because that actually kind of makes sense. The UI can't do things concurrently, and if you want to do work in background threads, that work should happen off the UI thread. So got rid of a bunch of mutexes. And then what we put in was a vizhit callback function, which had the logic for the vizhit function, which is what we had in the homework 6 starter code. So when we got a laser hit, it would draw it on the screen relative to the robot. The information that it needed was the range and the angle of the robot. So we go ahead and put that into a structure. We have a vizhit data structure that we're using just to pass that data from the robot thread into the viz thread. We're going to go ahead and allocate one of those, initialize it with the data that we got in the vizhit API, and then we're going to call GDK threads add idle. Let me zoom in a little bit so that maybe this is clearer. I at least can see better if it's zoomed in. Let's go even more. There we go. So we're going to call GDK threads add idle, vizhit callback with this hit data, and then the vizhit callback function is just the content that was previously in the vizhit function that actually went ahead and drew stuff called drawbrush to draw a dot on the screen where the laser hit was relative to the robot. So that's the main thing that I did in this particular patch. The other thing that I did is I sped up the build by rewriting the makefile. I got rid of cmake, because cmake sort of does optimization by default, and I didn't want to deal with it while I was developing. Just writing a simple makefile, sped up builds by around a factor of 2. And so we have a just GNU makefile here that just calls package config to get the appropriate flags, and then has relatively straightforward GNU make rules to build object files and then link them together into a executable file. So that's patch 1. Patch 2 was moving to the error model from homework 8. So my goal here was to create starter code for homework 8. The error model for homework 7 is a wonderfully interesting problem to have spent time with, but that's not the thing that we need here, because the stuff necessary to deal with that error model is not going to be necessary with the homework 8 error model. So to do that, we are basically bringing in the robot.cc from homework 8, just without moving to the camera. We're going to keep the laser sensor. So this is a patch that is going to, well, create some bugs, like not having that 50 there, but is going to go ahead and get rid of the raw x, raw y distinction from homework 7, pull out the homework 7 error model, replace it with the homework 8 error model, and then the thing that we're keeping is the laser sensor. So we end up with, let me actually just pull that up here, brain robot.cc. So the code that we end up with is, I mean, this is the latest version. We're going to have a laser scanner. We're going to have some error. So every time we do a set velocity, there's a little bit of error, so our robots don't automatically drive straight. But they don't have much error. It's just enough that you can't drive very far straight. And the other error that we have here is that we have pose error, but it's pose error that's random every time. So it's going to average out pretty quick. There's no drift in the pose error in homework 8. So that's the stuff that we're working with. Next patch that I did was to implement mapping. So in order to implement mapping, I went ahead and in our brain program, I added a module called grid where the mapping was going to be implemented. So that's a grid.hh file and a grid.cc file. And then instead of calling vizhit, which is what the homework 6 starter code does, I call grid apply hit. So I'm going to pass through this laser hit and the current pose of the robot, which I construct here from the robot data. And then we're going to, after we've applied all the grid hits, we get a view of the grid. We're going to show that view in our visualization. So now we have a map rather than just a couple individual laser hits. And then most of the rest of what's going on in here is just me removing prints so I can figure out what I'm doing. So the implementation of the grid is going to be that we have a coordinates type. The grid itself is a static global called grid, which is a map of a grid coordinate, an XY pair, to a integer. This integer is going to basically track how many times we've seen an obstacle in a particular grid cell. Utility function for debugging, being able to print stuff out is useful. Then we have the sort of interface to the grid. We have a get function, which will either find a value from the grid or say that there's 0. So this is an infinitely large map that's 0 by default until we increment the number of laser hits we've seen in a grid cell. Then we have grid put, which allows us to set a value in a grid cell. And then we have grid increment, which lets us either increase or decrease the value in a grid cell by some integer. And then we'll put it there limited between 0 and 100. So if we get to 100 hits, it'll never go any higher. We can't be any more convinced than having seen 100 hits. And misses are going to be count as negative hits, and so our minimum is 0. All right, so we have a constant. Let me find the header. Gotta be in here. Here we go. So we have two constants. We have a cell size. This is in meters. And so the initial value that I picked for that was every cell is a quarter meter, which is a relatively high resolution grid for the maps that we're dealing with. We could go smaller than that if the robot needed to get through really tight things, but mostly we have pretty wide open doors. And then we're going to have our view size, which is when we take a sort of GUI view of our grid, how many grid cells do we want to see? And in this case, it's going to be a 41 by 41 square. Just sort of arbitrarily, that's what fit in my display. All right, so looking back up at our grid implementation, we have a coordinate to key, which is going to translate locations in the world, X or Y coordinates, into sort of map indexes. So there's this sort of layer of indirection to be able to use integer keys, which we need for comparison. But the sort of idea here is that given a float X and a float Y, we can find the coords that is the key to get that map cell out by doing C to K on each of the coordinates and then doing make pair, which makes us a coords object. So in the brain module, we would call grid apply hit on every incoming laser hit. And what we do here is we're going to go ahead and make a set of the cells that the ray passes through. And to find that set, we're going to go ahead and just follow the ray and look every 0.1 meters to find the cells that we're impacting. Now we could miss a corner of a cell, not a huge deal, but this will tend to clear out, it'll give us the set of cells that we're supposed to be clearing out. The reason that we're using a set is because this 0.1 meter thing is sort of arbitrary and we're going to end up hitting cells multiple times, and hitting cells multiple times with the same ray doesn't really convince us anymore that the cell is empty. So we're going to figure out which cells we're looking at down the ray, and then we will decrement by 2 every cell. And the initial version that I wrote and tested with decremented by 1 when we missed a cell, incremented by 1 when we hit a cell, and I discovered just experimentally that I got slightly better pictures if I decremented by 2 for missing a cell, if it was on the laser ray but didn't have an obstacle. Then at the end, we're going to have the laser hits something, and we know that that cell has an obstacle in it, so we're going to calculate the key for that grid cell, and then we're going to increment it by 5, bump it up by 5, to show that it's full. Grid view. So grid view is an object that just stores a rectangle, like two-dimensional array with width and height. So we're filling that in. For every cell in the grid view, we're going to calculate the X and Y coordinates. So what we're displaying is a view of the map centered on the robot that's just 41 by 41. So we're just looking at the, I guess we have 4 grid squares per meter. It's 41 by 41, so we're looking at a 10 meter by 10 meter area around the robot, so the sort of 5 meter radius around the robot square. And this does the calculation to figure out what values did we see. And then the thing that we're actually storing in here is a floating point number, which is going to be between 0 and 1, like what percentage of hits up to 100 do we have. Sort of arbitrary, but this is the step that I took. The pose structure that we had got its own file. This is just an XYT like triple to make it a little bit easier to pass around robot poses. Looks like I deleted half of clamp in the old version and added it back in here. – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – or talking about lot guards, which wasn't relevant. And then we needed another drawbrush function in the visualization module that didn't just draw black dots, but could draw grayscale dots of various colors. And so we would do Cairo set source RGB and set a grayscale value. So instead of having vizhit, we're not calling vizhit anymore. The stuff that we're calling is vizshow. After we add stuff to the map, we're then going to call vizshow on the viz module, pass in that grid view that we had filled in, and it's going to go ahead and call GTK threads idle, and then this logic actually is going to draw our grid. And at this point, let me go ahead and run this so you can see what the pop-up looks like. Let me make sure that, yeah, all right, I have some arbitrary robot. Still a little bit slow to build, even though I tried to make it faster to build. Linking still takes time with this many libraries. Yeah, I'm not even sure that's drastically faster. I'm not optimizing, so I think it's a little bit faster. But now when I call brain here, E V there we go. So here's what the sort of grid ends up looking like once I finish it out. The logic that I'm showing here would just show the black, so like grayscale dots here as we hit obstacles. So this is the visualization that we're looking at. All right, there we go, back to my normal layout. So we're gonna draw stuff. Grid view, here's our like 2D array with get and put. It's just storing a float value for every cell in the grid. And so that got visualization of the map. So we could do mapping as the robot drove around, we generate a map and we'd see a picture of it. Next step I went through to get this to work is pathfinding. So to get pathfinding to work, in the brain module, the plan is first we're going to go ahead and call grid apply hit on every laser hit. Then we call grid find path, get a path from the robot's current position to our known goal position, which is at 0, 20. Then we're going to ask for a grid view and do viz show. Now here we move from a grid view to a mat, an OpenCV mat. And that's because I wanted to be able to do colors other than grayscale, and rather than reinventing the wheel on a sort of RGB image, we're just going to use OpenCV for that here. So grid view returns a mat now. Now in order to do pathfinding, we need to implement a star. So that happens here in grid. Path is a sort of another static global variable. It's just going to be a vector of coordinates, a vector of cells in the map. And this is something that we're, when we do pathfinding over here, this doesn't return a path, it just sets the path in the grid module. And then when we run it again, it will set a new path. This could use some work on threading it, but it appears to run okay on this particular computer. As you add in computer vision or stuff, you may need more threads. So now grid view is going to take a pose and give us a mat instead of a grid view. And mostly what's going on here is that we are translating this to use a mat instead of a grid view. But the other thing that we're going to do is we're going to go ahead and create a set of all the cells in our path. So as we go through here, in addition to setting cells to be sort of grayscale, whether or not there's a wall in that cell, we're going to ask, is the cell that we're looking at on the path that we've calculated? If so, we're going to draw it blue on the visualization. Now, A star is a little bit tricky. What we need to do, here we go. So here's A star. So to find a path on the grid from a start position to a destination position, the procedure is we initialize a set of things that we have seen. So we're only going to ever worry about a cell in the grid once. If we visit a cell in a grid a second time, having gotten there in a different direction, we're not worried about it because the second way we find something is always a longer path than the first way that we find something. Same argument as Dijkstra. We're going to have a queue, and this is a priority queue based on heuristic cost. The heuristic cost in A star is the distance that it factually took to get there as we found a path, plus the distance from the cell that we're looking at to the destination, just straight line. But we need a priority queue structure that is able to prioritize based on a parameter, and the way we're doing that is with a C++ priority queue, which we can parameterize on contents, and then a operator that can look at two objects in the thing, two search cells in this case. A search cell contains a cell coordinate and then the distance from that to the destination. So yeah, we are using that as our queue. We're going to have a map of costs for cells that we found a path to. What is the cheapest path that we found to them? And then we're going to have a map. So for every cell we visited, how did we get there on the cheapest path? And that's how we'll, once we've gotten to the destination, build back up our list in the other direction. We'll start by inserting into our queue of cells to look at the cell that we're starting in. And then what we do is just until we run out of cells to look at. If we run out of cells to look at it, that means there's no path. We're going to pop the cheapest looking, so most promising cell off the queue that we haven't looked at. We're going to ask, is that the destination? If it's the destination, we're done. Otherwise, we are going to ask about the neighbors of the cell that we're looking at. For each neighbor, if we've seen it, we're just going to skip it. If we haven't seen it, we're going to insert it into the scene list. We're going to remember how we got there, store that in previous. We're going to determine what we think it costs. We're going to add that to our costs table. And then we are going to, and I suspect this may be buggy A star. You should double check this. But it works well enough to create paths for the demo, so it's starter code. Then we're going to get the occupancy data from our occupancy grid. We're going to calculate a score based on, and if it is blocked, we're just not even going to consider a path through here. We can't get there from here if we don't go through walls in this version. So then we're going to calculate a score. And we're going to push a new search cell onto the queue, which is the neighbor prioritized by this score, which is the cost that it took to get to our source cell, plus the distance from the neighbor to our destination. So once we go through this set, we're going to clear our path, whatever it was. If we broke out of the loop without having found a destination, without having gotten to the destination, we're going to print out a message saying that we're confused. Otherwise, we're going to push the cells onto we're going to start at our destination and then traverse through this previous map, finding the previous cell all the way back to our start point. That gives us our path backwards, we reverse it, and that is our pathfinding. Other stuff that's going on here, we have to be able to draw visualizations that aren't just gray. So we'll take a like RGB pixel and draw it. We have some debugging in the viz show callback here. We have to do some updates to move to a mat, to include our mat header here. We had got to completely get rid of this grid view thing, didn't even need it. And so that is pathfinding. Finally, I wanted the robot to be able to drive to make sure that this made any sense, so I made a really bad obstacle avoidance. And so the changes I made for really bad obstacle avoidance are, in the robot callback, we're adding some logic where we can get our goal angle by asking the grid module. We pass it our pose. The grid module knows our path. We don't know our path here, so it's going to pick a location on the path and figure out the relative angle to that. We're going to figure out which direction we want to turn to look at that. Then we are going to, if we're not facing in that general direction, we're just going to turn towards it. If we are, if we have no obstacle in front of us, we're just going to sort of drive forward and turn in the general direction towards our goal. And then otherwise, if we have an obstacle in front of us, we're going to try to avoid walls. And we're going to try to avoid walls in a way that hopefully makes progress. This doesn't work very well. So there's some other changes in here that are specifically to make this awful obstacle avoidance code work better. We have some ability to translate a coordinate back into XY floating point values, because these integers that we store in coordinates aren't real coordinates, they're in grid cell sizes. We need a neighbors function so we can find neighbors. Oh, we had a neighbors function in the original pathfinding version that we just looked at. Here we're expanding it to be a neighbors function that gives 8 neighbors rather than 4 neighbors, because that gives like slightly better paths. The other thing that we're doing here is whenever we apply a hit, we're going to increment the target that we hit by 4, but by 8, but we're going to increment all of its neighbors by 4. So we're gonna put walls where there aren't any. That's in order to try to make our path following obstacle avoidance work better, so that we tend to get paths that aren't right next to a wall. Another thing that we do here is when we're A-star searching to find a path, we're going to go ahead and apply a penalty in score to neighbors of things that are obstacles. So this is giving us a sort of 2 grid cell buffer. And a 2 grid cell buffer ends up being enough that this robot can drive around a little bit. Here we have logic to calculate our goal angle based on path information. And the way we do it is we're going to try to look at path sub 2, so not the first, not the second, but the third cell in the path away from us, and hope that it's not so far around a corner that we run into trouble. This will calculate the angle of that, and we return the robot relative angle, basically just the direction that the robot needs to turn. We're also increasing the cell size from 1/4 meter to 1/2 meter, which again makes things a little bit chunkier and makes it so we don't drive quite as close to walls. Also, it makes everything cheaper because we have bigger grid cells, and so all the computation is on a sort of smaller data structure in memory. All right, so there is a sort of more complete starter code for the homework. Let's go ahead and look at this awful thing run. I'm not claiming that this was a good solution to homework 7. I'm claiming that this has a lot of the pieces that we need. And specifically, the thing that I'm claiming is that if we look at how many lines this is about 1,000 lines of code, including the robot code, whereas I haven't even tested this, but yeah, Joe's solution was about 1,600 lines of code, so that's mostly why I wanted to make this, because I think it might be a simpler starting point. It may not be. You may want to start from Joe's code. You can do that if you want. That's why I put in 2. But yeah, we want to go ahead and try this. So I'm going to run brain. It's going to pop this thing up again. So here's our grid. Blue line is the path. Let's pop this over to our thing here. Make me smaller. Make the, I guess this wants to be on that side. So the robot is sort of slowly turning, and up here is the same as up over here. If we have like the goal to the, I mean, that's the wrong direction. The goal to the right. If we have the goal to the right, then the directions on the visualization are the same as the directions in Gazebo. You see the blue line is the portion of the path that we can see on our map. You could make this visualization bigger. I just made it super small for my own personal convenience. You can see it's sort of trying to get through that door because that's the best path it can find at the moment. We're driving through the door, and then the robot sees that it has a nice clean shot to the goal. We can see as humans looking at this map that it does not have a nice clean shot at the goal. But let's just watch it get confused and see how it recovers. With OBS running, I only have a sort of 80% real-time factor. Not sure why Gazebo is running so slow. This shouldn't be that difficult a thingamadoo. All right, so we drove up, we found a wall, and we're sort of driving along this wall, trying to see how we can get around it to get towards the destination. Now, I wonder if the goal that we're going towards is even correct here. It may not be. It looks like we might be going for a goal up here, which is not actually the thing that we want, but it's still the same problem, so that's fine. Well, you can see how this works. This is the sort of apparently broken starter code that I'm giving you. Good luck with homework 8, and have fun.